Yes.
Can I get everyone's attention? So, Crash is going to be starting soon. He's going to be doing our Steels workshop. So, could everyone give him a round of applause, please? Just a few things. We're going to record these. So, my computer's up the front here. It's going to be recording the whiteboard. Everything on the whiteboard. Yeah, Crash is going to be doing most of his working on the whiteboard and stuff. And yeah, that'll be uploaded to our YouTube channel, and then that link will be shared throughout the stuff like Instagram and Facebook pages. So please make sure to follow those. And for anyone who hasn't scanned the QR code, I'll just hold it up for the moment. And yeah, if you could just give us a scan, that'd be really good. Otherwise, I think that's everything. You can just take it away.
Okay. Do you want to close the door? All right, everyone. We'll get started with the Steels workshop. Now, I think what would be best to do is probably like an in-depth look, recap of how to do beam column design, right? Because the good thing about doing beam column design recap is we basically cover everything from tension to compression to bending to combined, right? And then at the end, the only thing you wouldn't cover in beam column design would be connection design, right? But once we've done beam column, if there's still some time remaining, then we might do connections. But if not, then I might not be able to cover that. But just doing beam column hopefully would be useful to at least 60 to 70% of your revision. Okay, because it covers beam column topic covers everything from the start. Okay, so let's give a particular example. So say you have, so this is, okay, I'll start here. Okay, so beam column design. Okay. Now, the example that I'll give you today, let's say it looks something like this, right? I'm just gonna give you like a part of a beam, a part of a column, okay? And let's say, the column goes through, it's got compression. So let's say the axial force diagram for the column looks like this. Negative 50 or something, whatever, for example. This is the AFD. And then the bending moment diagram of the column looks like, let's say, something like this. Okay. At the end of the day, any beam column question that you get, right? Always try and identify what are the stresses or what are the forces that are being applied on the element that you're designing. So sometimes the question might start off like this, and say, oh, by the way, you've got this huge building, design this particular column, and this is the bending moment and shear force or axial force diagram for that column. Now, most of the time they don't give that to you because that'd be too nice of them. So whatever loading they might give you, etc., from the different workshops that you've done in the course so far to try and calculate what those forces are. At the end of the day, remember what you need before you start your step-by-step is you need your axial force diagram, okay, for your column, and you need the bending moment diagram. So what makes it a beam column? Remember, at the end of the day, a beam column is a column. But the reason why we're adding the word beam in there is because it's also bending, right? So apart from the axial force diagram, we also have the bending moment diagram. So remember, your first step is to identify these two, okay? Once that's done, then we can start with the step-by-step. So the first step is to determine your design actions, okay? So this is step one. Determine design actions. So what does that entail? That entails drawing out your axial force diagram. That also entails drawing out your bending moment diagram. Okay. What that also means is, I want A star, or however you call it, N star, for example. That's the axial force that we're going to use, and M star. These are the values that we need, right? This is the design action for your values. Now remember, The other thing to take into account is your load combinations and load cases. Okay. Now remember, when you're doing an ultimate design for a beam column situation, right? You're using the ultimate limit state. Okay. So you need to run through all of the different load combinations, right? What are some of them? 1.2G, 1.5Q, 1.35G, and generally for a beam column question, your bending is coming from something like wind, right? So what that means is, what load combination would you be using if there's wind involved, right? There's two types of load combinations if there's wind. One load combination is if you're, your 1.2G and then you've got Q in there as well, and then you've got wind. The other load combination is for wind action reversal. Okay, what does that mean? So the reason why there are two wind combinations in the code in AS 1170, okay, by the way, your load cases and load combinations are from AS 1170. Okay, even though the design is all according to AS 4100. Now, just remember, when it comes to wind, there are two load cases that important load cases we need to consider. Not the only two, but the two that are specific for wind. You have your standard wind case, standard wind condition, and then you have wind action reversal. Okay. Now, the reason why there are two is because one of them is used for if you have wind that's blowing in a direction that's similar to the gravity direction. Okay, so I'll give you an example. Let's say you're designing a roof, right? And you've got your two columns here. That's your beam that's supporting a roof, right? If you have wind that's blowing down on the roof this way, and you have a roof loading like this, everything's pointed in the same direction downwards, right? So what is the worst effect? The most adverse effect is if your gravity loads and the wind and the live load, everything is pointing in the same direction. That'll give you the most adverse effect for that, right? So that is this case, okay? Now, when do you know if it's a standard condition or if it's a reversal condition? A standard condition is where your dead load G is higher than 1, the factor for your dead load. So for example, if you've got a dead load of, like if your dead load factor is 0.2 or 1.2, something like that, that is because they're aggravating what the dead load is. Wind action reversal was made for the case where you have wind uplift, which is the other way around. So for example, let's say again you're designing the same roof, but this time around you have your dead loads coming downwards, your live loads are also coming downwards, but your wind is blowing upwards, for example. If that is the case, what you'll generally tend to find is for lightweight structures, and most of the time, when you're dealing with a steel structure, it's usually a lightweight structure, right? Most of the time, when you have wind that's blowing on a steel structure, the wind ends up being one of the most significant loads that it encounters, right? You see, imagine if you have a significant uplift load here. What the wind action reversal load combination does is it does 0.9G plus W, and I believe it's something like that, or there might be something else. Have a look at the code to confirm. But basically, that's what it looks like. You have G, your factor for G is less than 1, it's 0.9. Okay? So what they're trying to do is they're trying to not aggravate the dead load component, right? Because the total action of this wind blowing up is actually upwards. Okay? So you have to consider that as well. And usually when the wind load is given to you, right? If the direction isn't specified, then you have to do two cases. Assume it's blowing in one direction, and then assume it's blowing in the other direction, right? Now, for a beam column, if your wind, remember, if the wind is blowing upwards, so let's say this is the roof. This is the beam column I'm designing. If the wind is blowing upwards, using the wind action reversal combination, that might put my column into tension. It's possible, it's entirely possible that your axial load is actually, negative, which means it's, going the other way, so it's in tension. Puts your column in combined bending and tension. That's entirely possible. It's rare, but it's possible. Okay. So anyway, that's an important point that I want to draw to your attention. make sure you don't miss out on any load combinations. So for example, if you have dead loads, live loads, and a wind load, what are your load combinations? 1.2G, 1.5Q, 1.35G, and then you've got two wind combinations, standard wind condition and the wind action reversal. So you go through all of these and pick out the worst case scenario, and that's the one that you use. Now another important thing that I want you to remember is when you're collecting these forces, when you're collecting N star and M star, please note that both N star and M star have to be from the same load combination. Okay, so I'll give you an example. Let's say in one of your load combinations, you had N star and M star being a certain value. And another load combination, you had another N star and M star. What you don't do is you don't go, oh, from load combination A, I'm going to pick N star from here, and then from B, I'll pick M star from there, and then put them together. You can't do that, okay? Because it's too unfair to the system, okay? If you're saying that N star and M star, these are my values that I'm going to use to design my building, you must remember that they both must be coming from the same load combination. If not, it's not realistic, right? You can't get N star, which is in tension coming from wind uplift, and then M star, which comes from the standard wind case. That'll never happen because those don't happen at the same time, okay? So for example, so let's say from load combination A, N star is 4 and M star is 5. And from load combination B, N star is 1 and M star is 3. I'm giving you very unrealistic simple numbers here, but I'm just going to explain this, right? Obviously, if this is my situation, I'm going to choose A, right? Because both of them are higher. But let's say, for example, this is what I have. Load combination A gives me 4 for N star and 5 for M star. Load combination B gives me 6 for N star, but 3 for M star. I wouldn't know which one to use, right? So you would have to test both, right? So N star, M star for one of the load combinations, right? You do load combination A, and when it comes to your calculation where you're comparing between your capacity factor and your capacity and the actual design action, you would need to try both. That's a sneaky way to get you, but remember that's the concept behind it, okay? The key thing behind here is you must know that for different axial or for your different design actions, they can't be coming from different combinations. It doesn't make sense. Okay. Any questions on this? Cool. All right. Now that's step 1. All right. So step 1, by the way, includes analyzing the structure, and then calculating cases and combinations, and then you get this. So in fact, this is step 1 and 2 really. If step 1 is determining what load combinations and cases you're going to use, step 2 is analyze the structure and do your bending moment, ship, axial force diagram calculations. That's all step 1, step 2. Okay. Now, step 3 is accumulate required data. So what's the required data that you need? Okay, by the way, it's much easier to do a beam column design question if you have all the information that's ready to use rather than struggling through one steel to try and find what all these numbers are while you're doing a question. Okay, so I'd always recommend when you're going to start doing the question, just use those values. So what are the values that you need? You need N star, Mx star, My star. That's your first level. So that's the axial force. And remember, bending moment can be in 2 directions, right? You've got your bending moment in the X direction and the bending moment in the Y direction as well. Because this is a beam column question and it's usually a bit more complicated. They would have given you forces in 2 directions. You need those, okay? So accumulate those forces. The next thing that we need, by the way, can everyone see what I'm writing here? Yeah, okay. The next thing that you need are the lengths, okay? Specifically, you need length in the X direction and you need length in the Y direction. Okay? And then you need your section data. So this is Section data is from one steel catalog. Okay, the section data that you'll need, IX, IY, you will need Z effective in the X direction, Z effective in the Y direction. The radius of gyration in both directions, Rx and Ry. And you need AN, KF, J, and IW. So remember, AN is your net cross-section area, KF is your form factor, and J is your polar moment of inertia. IW is again has to do with twist. Okay, it's like all based on warping. Okay, so those are all the section data that you've got to take out. Okay. Now the important thing to remember is what is the difference between L and LX or LY. Okay, so remember L, maybe I'll just write here. L is related to the full length between full restraints, partial restraints, or lateral restraints. Okay. Now, a very important part of this topic and beam bending topic is to understand what are the differences between your full restraint, partial restraint, and lateral restraint. Because sometimes the questions can say what they are, and sometimes they can't. They won't. Okay. So if a question doesn't tell you whether this is a full restraint or a partial restraint or a lateral restraint, but it just shows you what the connection looks like, it's up to you to actually decide what it is based on it. Okay. So have a look through the notes, have a look through the code AS4100. There are point forms that are given to you of what constitutes a full restraint, what constitutes partial, and what is lateral restraint only. Okay. The important thing you've got to remember is what is the critical flange. Okay. So if I just ask everyone now, just as a recap, if you have a beam that's supported on both sides, right? So you've got two pin supports on each side, and there's a downward load. Can anyone tell me which flange is the critical flange? The compression flange on the top or the tension flange on the bottom? Compression flange. Okay. What about for a cantilever beam that's fixed on one side and free on the other? You have a load that's applied downwards, so the entire thing bends down. Which is the critical flange for a cantilever beam? The top tensile flange or the bottom compression flange? The tension flange? Tension? Are we sure? Okay. So if I draw this out here, just quickly, what I'm really asking for is, that's your beam, yeah? You've got a UDL that's across this entire thing. What's the beam going to look like when it bends? It'll do something like that. That's what it looks like when it bends, okay? From this part to this part, in this segment, your compression flange is what? The top or the bottom flange? Top flange, okay. Compression is on the top flange, okay? This side here, where's your compression flange? The top flange or the bottom? Bottom. Compression is on the bottom flange. But for a cantilever segment, what is the critical flange? Compression or tension? Tension. The tensile flange is the critical flange for a cantilever segment. So for this segment here, the top is in tension. So I'll just write this clearly. Critical is top flange. Here, critical is still the top flange. Okay? Why? Because the critical flange is the tensile flange for a cantilever segment. For a segment that's supported on two sides, the compression flange is the critical. Okay? So keep this in mind. Okay? Now the next thing is, yes, you've got to know what it looks like, right? What are some possible examples of a full restraint? What are some examples of a partial restraint? Those are given in the code, AS4100. So if you have AS4100 with you, just have a look there. They would have given you different sketches of what different types look like, and I'm sure the lecture notes has some examples as well of what some of these different section details looks like. Okay, So remember, short of them actually telling you what it is, sometimes it might be shown and you need to figure it out. So remember, the length here that you need to calculate or you need to get is the full length between F, P, and L. And Lx and Ly are the length between your column buckling restraints. Okay, this is really important. Okay. All right, let's go to step. That was step 3. Okay. By the way, this is all from One Steel. Yeah. Now let's go to step 4. Step 4 is you need to calculate what the effective lengths are. Question.
So is it, so you said for a cantilever, does that mean like partially restrained, or is it just like
So a cantilever segment is made up of one side being either fully or partially restrained and the other side is unrestrained. Yeah.
And then that would be the compression, no, the tension.
The tension flange will be the critical flange, yes. Okay. By the way, another important thing to note when you're doing beam design is asking yourself or knowing for sure what segments to check and what segments to not check. Anyway, when we come to the beam design portion, or the flexural design portion, I'll pause and I'll give you some quick recap on which segments to choose from, okay? And how to define segments and sub-segments, that's really important. And then figuring out which one's the critical segment. Because if you really want to design a steel section for flexure, the most inefficient thing you can do is check every single segment or sub-segment, okay? Especially under the time crunch of an exam, the point is to test whether you can look at what's given to you and figure out which one's the most critical one, and then you check the most critical one. If you size it for the most critical one, then you're good for the rest, right? So I'll go through that later. But anyway, let's have a look at the effective length. For effective length, we need them both in the x and the y direction. Lex is equal to Kex times Lx. Ley is equal to Key times Ly. Okay? Now, where do you get your effective length? Remember, in the course, there were 2 versions of this that were covered. The first version is a simple one. So by the way, this is from clause 4632 or 4633. Okay? Now that was gamma method. Okay? There is also simplified method, which was discussed, or rather the idealized method. So remember, how do you do an idealized method? For idealized method, generally that's in the case where the question doesn't give you the entire frame, it just shows you one column, and it tells you, simply put, the column is pin, pin. Pin on the bottom, pin on the top. Okay? So what is your, in a pin, pin case, is your effective length equal to the total length of the column? In a pin, pin case, the effective length of the column is equal to the length of the column because K is equal to 1 for pin, pin. Remember? If you have fix, fix, what's K equal to? Sorry? 0.7, okay? And then if it's pinned on one side, fixed on the other, it's 0.85, and so on and so on and so on. So in the idealized method, that is if you're able to say correctly, the bottom is pinned, the top is fixed, or whatever, okay? That's the idealized method, or also known as the simplified method. But most of the time in a beam column question, they've given you they've drawn out the entire frame for you in 3D, okay? If you know exactly what the frame looks like, that means I know that this column which I'm designing has a beam coming in this way, has a beam coming in this way, and I know what the sizes of these beams are, etc. You cannot use the idealized method anymore. You have to use the gamma method. The gamma method's a lot more accurate in calculating what the effective lengths are. Remember, all of this is just for step 4, effective length, okay? So if you recall, how to do the gamma method, essentially, for a particular column, right, using the gamma method, there's two important nodes. You have your node at the top and you have your node at the bottom. Okay? So gamma for a node can be either top or bottom. The gamma for a node is given by the sum of I over L for all columns over the sum of beta E times I over L for all beams. Okay? So you can do this for the top node and get your gamma top. You do this for your bottom node, get gamma bottom. And once you do that, you use these clauses to calculate what KE is. Okay, and that'll be KEX. Then you can do the same thing in the y direction, get KEY. Okay. Again, I'm not going to spend too much time on this because I believe there was an almost entire week that was devoted to just gamma method. But this is just a recap. This is what it is. Okay. Important thing to note is beta E. Be very careful to choose the correct beta E when you're doing this question. Okay. Pay attention. So what is beta E based on? It's based on two things. Beta E is based on what is the connection of the beams on the close side to the columns. But beta E also depends on what is the connectivity of the beam on the far end. That means on the other side, right? Is it fixed into a wall? Is it pinned over there, etc.? Okay. So based on these two, you can select your beta E parameter and make sure that's used in your calculations. Okay. Just be very careful. Revise exactly what the correct beta E is to use because it's a waste to do all of these questions and get all the numbers correct and you got it wrong because beta E was wrong. Right, that's pretty simple.
Another question. What are the cases where beta E is 0? Because they didn't really mention it in the lecture.
Okay, so let me just recap that. Okay, so remember, beta E can be gotten from table 4634. Okay, and that is primarily asking you what's happening on the far end of the beam, right? So if you use table 4634, you will identify what beta E is based on what's happening on the far end. Is it pinned? Is it fixed? You know, etc. Okay, but you also need to remember that beta E equals to 0 if the near end of the beam is pinned. That's very important to remember. Okay, if the near end of the beam is pinned, right, to the column, it means that any bending that happens in that beam doesn't affect the column at all, right? Whenever you pin something, you've basically isolated those two parts of the structure. So if the near part of this beam here, for example, is pinned to this column, then beta E is equal to 0. Okay, because the column doesn't feel anything that's happening with that beam. If the beam wants to rotate, it'll just rotate. That's it. Okay. Beta E only has a value if the beam here is fixed in with the column. Because whatever bending happens to the column will be felt by bending happens to the beam is also felt by the column. So that's why it matters. Beta E matters. Okay, but if they are both isolated, which means if the near end is pinned, then this just goes to 0. Usually the calcs are easier to do when everything's pinned, right? Because then a bunch of stuff is all 0. Anyway, that is the gamma method. Any questions on this? Yep.
Yeah, for beta E, I think there's also like in the table there's like the beam restraining sway member or beam restraining.
Yeah, correct. Correct.
How do you differentiate like which one?
What is braced and what is sway?
Yeah.
Is that a question?
Yeah.
Okay. All right. So that's a very good question. So let me give you an example, right? Yeah, just like that. Okay. Load is applied here. Is this a sway frame or a brace frame? Sway frame. Did someone say brace? Okay, it's a sway frame. Okay. All right. Sway frame or brace frame?
Sorry.
That's good. That's good. Okay. All right. Okay. Now I'm going to make it a bit more complicated. Let's draw. I'll draw you the plan in plan view. What the frame looks like. Okay. So let's say column, 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 column. Okay. Does everyone understand this drawing? Yeah. You've got a bunch of columns that are moving into the page, and you've got all these beams here connecting everything up. Okay. Right. Now. There's a brace here. Does everyone understand what this is? Right? It's a brace down. Yeah, it's a cross brace downwards. Right? So let's call this frame A, frame B, frame C. Can everyone answer me? Is frame A braced? Yeah, but okay. So whenever the code refers to a frame, right? Whenever a code refers to a frame, so like this, right? The loading that's assumed on that frame is always across the page. We never refer to a frame and talk about loads that are moving into the page. Okay? So for example, if I'm asking, or if the question asks, or the code is referring to a frame that is braced, they are referring to, is the frame braced against loads acting this way? Okay? So for example, if I'm asking, is frame A braced, I'm asking, what I'm really asking is it braced against these loads? Okay? If you're worried about loads going the other way, then I shouldn't be talking about frame A. What should I be talking about? Frame 1, 2, and 3. Right? Okay, so again, if the question here is frame A braced? Is it? Yes. Frame A is a braced frame. Okay. Now, let's say, so remember this is the ground floor, right? If you move up to the first floor, let's say on the first floor you have your flooring that's connected here. Okay, to make your building walkable, right? Then you've got some flooring here. And let's say this flooring is light framed flooring or something like that. Basically it's not a material that's very stiff. Okay, like timber or something like that, right? See, let's say this is light frame flooring. Okay. Is frame B braced? Yes or no? No? So basically what I'm asking you is, if you apply a load here, is frame B going to operate like a braced frame or a sway frame? Why?
Just like a wall, just have a wall. If you put the forming here, it will be defended by the wall, so it's braced.
Okay, so you're saying because A is braced, you're saying B is also braced.
Actually, no, it's because the wall defends the force, so it's braced. The floor. The floor.
Sorry, not the. Sorry, say that again, sorry?
There are light floor flooring.
Yeah. You're saying because of the flooring.
Yeah. Because it's the flooring, so
It's
the
braced.
force from B this side is again defend. So it's
Okay, I understand what you're saying. So when you have a force here, so the explanation here is when you have a force here, right? What is bracing this frame is the flooring,
yeah.
right? And because this side is braced, so okay, let me flip the question and ask you again. If there is no bracing here, is this a brace frame or a sway frame?
braced.
That's where the problem is, because remember, if there's no brace here, you just have flooring here, right? That's like saying this is your frame. You have flooring here, but that flooring is not stopping any movement in this direction. The whole thing can still sway.
Yeah.
You need something to do that, right? So you need a brace, okay? So I'll ask again. Let's say frame A is braced. There's no bracing in frame B, but there is a lightweight flooring that's connecting all of this together. The question is, you already know that frame A is braced. Is frame B braced, or is it a sway frame? Sway. Why?
If you put a force
Yeah.
on the left, wouldn't the B columns like deform a bit?
Yeah. So you're saying if I apply this force here,
Oh no, it's
Or
saying
the
put
other way.
force on the left. Oh no.
this way.
Yeah, that way.
But remember, again, what I came back to earlier, whenever the code asks, or the question asks, or you asking yourself, is a frame braced or sway? The question is it braced against movement across the page? So for example, if I'm talking about frame B, which is this frame, right? I'm really referring to forces like this. So remember, this is plan view. So these columns are sticking out of the whiteboard, right? These columns are sticking out of the whiteboard. So I draw this up for you. What this looks like in 3D is this is what I just drew here. Okay? What I've drawn is plan view, which means top down. Right? So these are all the different columns. That's the view, that's the top down view. Right? So when I'm referring to frame B, in this case, I'm referring to this frame. That's frame B. Yeah? And I'm asking you, is frame B braced against movement like that? Right? Now, so that, okay, no, right? Okay, the correct answer is no, it isn't. It's a sway frame. Why is B a sway frame? Because A is a braced frame, right? B isn't braced, there's no bracing here. C is also not braced. There's no bracing here, right? Now, the question that you've got to ask yourself is, what is connecting this, and this? Right? I've said it's light frame flooring, or lightweight flooring, or however you want to call it. It means that it's a flooring that isn't stiff. Okay? What that means is, it's squishy, it can bend. So what that means is, if this frame is braced, it means that this frame isn't going to move. Okay? This frame is going to stay still no matter how much force you apply here. What about this frame?
Move independently.
Yes.
It's like on a beam, so the beams can sort of like AB can bend per
Correct.
se with the wind. So it's
Exactly. This whole thing can move independently up and down with this staying the same. Okay? So this is a sway frame and this is a sway frame. Okay? But what if this is not lightweight flooring? Let's say this is concrete floor, a thick concrete floor.
will they all be? Will
Yes.
they also be braced? Will they be braced because that floor, if that floor starts to move, that's gonna like essentially break that floor because it's a concrete.
Exactly. That's exactly it. If your floor is stiff enough, right? If you've got a stiff flooring, you've connected this frame, and this frame strictly together. It means that if there's a brace here, this is also braced and this is also going to be braced. Because if you try and push this frame won't move independently of this. They'll both want to move together, right? But because this is braced, this will also be braced and this will also be braced. Okay. So that is if you've got a concrete floor. Another version of that is called rigid diaphragm. Okay? If it's mentioned to you or you know that the flooring is a rigid diaphragm, it means that it's rigid, it means the floor is rigid, it's stiff. The other thing is, what's a diaphragm? A diaphragm is basically any element that resists loads like across a floor, basically. Okay? So whenever someone says mentions diaphragm, what that means is they're referring to the floor that is resisting forces moving across the floor this way. Because usually when we design a floor, we're designing it for gravity loads, upwards and downwards, right? But if the floor is going to resist loads shooting across it, that's diaphragm action. Okay. If it's a rigid diaphragm, they are all braced. Everything is braced. Okay. But remember, if this is a concrete floor, is frame 2 braced or swayed? Frame 2 is swayed, because nothing is nothing is braced in the x direction, right? As in from left to right, nothing is braced. The direction that's braced is only this way. Okay. Anyway, that's really important. So, based on whether it's braced or swayed, use the correct clause, identify the correct gamma value. Any questions on this? Gamma. Again, I really recommend practicing gamma method, because if you get a beam column question, like 9 times out of 10, your effective length calculation is going to be a gamma method type calculation. Especially if you only have 2 questions in your exam, right? Anyway. Okay. Yep.
For the columns, when we're doing the gamma method, are we using IX or IY?
So it depends on which direction you're looking at. If you're using the gamma method to identify the effective length in the x direction, then you're using IX. But then you've got to do the same thing for y anyway, because you need these two. Yeah. Okay. So remember, for the design of the column using beam column, you need to analyze it both in the x direction and in the y direction, because you need both. Okay. Now the next part of this is pull this up here. Okay. Now, once we have gotten our effective length and we've completed the gamma method, the next step is we need to amplify our bending moments. Mx star and My star. Okay? Now remember, for braced or sway, we have 2 different types of moment amplification factors. For braced, if there's no compression or tension, then the amplification factor is equal to 1. Okay. If you have compression, then the amplification factor equals to Cm over 1 minus n star over NOMB. And recall NOMB is equal to pi squared I Okay. Again, this is something that's already in the code, so if you can't see from the back, or you can't copy, don't worry about it. It's something that should be already in your notes. This is how you apply your moment amplification factor for a braced column. This was also covered in, I believe it was sometime in week 4 or week 5, somewhere around there, where you've done compression design using the gamma method. This was part of it. Okay, you need your amplification factor. Okay. And then there's also for sway columns. Okay, if you have a sway frame, the way you calculate delta S, which is your moment magnification or amplification value, there's a couple of formulas that you need. First is NOMS. Okay, I'm not going to write out the entire formula. But then this is the basic form of what you need. Okay, so calculate your norms for the sway column. You already have your n star, which you've already collected at the start. Calculate lambda ms. There's a formula in your notes to calculate lambda ms. That's the slenderness, essentially. And then you calculate your amplification factor. Okay, that's the, basically it's to take into account the amplification that happens to the moment because of buckling. Okay, or second order effects, basically. So that's step 5.
Sorry.
Yep.
I think it was in week 10. There was like a lecture, there was an example where he found both brace and sway, right? So in this case, would you use both
You mean to amplify the moment there's
Yeah.
both braces?
Both.
Yeah, because it's entirely possible that in one direction it's braced and in the other direction it's swayed. Right? So if in one direction it's braced and in the other direction it's swayed, for example, right? Then what do you have to do? For the direction that's braced, whichever it is, let's say MX is braced and MY is swayed. Okay? Then for MY, because it's swayed, you use the sway part. And then for MX, because that direction is braced, you use the braced one. Yeah, you just use the appropriate one. Okay? Although generally speaking, the direction that's braced is always the weaker direction, which is the Y direction. Okay? If you ever get a question where you're like rolling through your calcs and you're like swimming through everything and it's super easy, and what you're actually doing is the Y direction is sway and the X direction is braced, just stop yourself and just do like a sanity check and double check that that's exactly what's happening. It's so rare, you will very rarely see that because you're missing the point of the brace. Bracing is to strengthen the weaker direction of the column. So if you're only going to brace one side, you'll brace in the weak direction, right? You won't brace in the strong direction. Okay, so that's step 5. Okay. Step 6 is calculate the slenderness reduction factor. Alpha C. This would have been covered in your compression during the compression topic. Okay, that's just basically from your notes again. And then step 7 is your axial capacity. Okay, I'm giving you the compression formulas here, but again, like I said, if you're designing for tension, then you got to use the tension formulas for axial capacity, right? So I'm just going to give you the example here for, remember, the section capacity is determined as Kf, An, Fy, and then the member capacity Nc is determined by alpha C and S. Alpha C is your reduction factor, okay, to take into account the buckling. And so at this stage, you check N star lesser than or equal to phi Ns, N star lesser than or equal to phi Nc. So if you get to this stage, then you've done your axial check, okay? So what you've determined is your column under compression loads is safe, both in the section sense and in the member sense, okay? But remember, compression or tension is not the only axial force it's experiencing, right? You also have bending. So the next stage of your calculation is going to be all the bending related stuff, okay? So now let's do step 8. Now for bending, there's 2 strengths that govern, right? The first strength is your section capacity for bending, and the next is your member capacity for bending. So section capacity for bending, so nominal section capacity for bending is MSX, which is ZEX Fy, and then you have MSY, which is ZEY times Fy. Okay, so basically your section modulus Z multiplied by the yield strength F Y will give you your various capacities. Okay, step 9. Now, at this point, you need to check the member capacity of your beams, right? So for example, if your element, your beam, right, or column in this case, if it is completely laterally restrained all the way across, do you need to find the member capacity, or do you just stick with your section capacity? Okay.
It's fully restrained, MBZ for NS.
Very good. So if it's fully restrained, basically it's not going to buckle, right? So the section capacity governs, so MS, right? or your MB calc is basically MS. Yeah. So if it's completely laterally restrained, but if it is not continuously laterally restrained, is there a way for you to check whether the code allows it to be continuously laterally restrained?
The L over Rx less than 80 plus 50.
Very good. There's a clause in the code which basically says if there is a spacing between your lateral restraints, if that spacing is close enough, if it's close enough, you might be able to just say it's pretty much continuously laterally restrained. Right? How do you do that? There's a line or two of formulas in the code that you've got to calculate, and if it clears that clause, then you take it as continuously laterally restrained. Okay? If it doesn't clear it, then it means it's not continually laterally restrained, and you need to find the member capacity. Okay? So step 9 really I would say is check member has full lateral restraint. Okay? By the way, that clause that I was referring to you to check is let me see here. Have you got it?
Do I, you can have it somewhere, hang on. 5.3.2.1.
Yep. Okay. So check whether a member has full lateral restraint or not. Use clause 5321. Use those formulas to figure out if it is in fact continuously laterally restrained.
So it's 5.3.2.4. Sorry.
Okay. So if it is continuously laterally restrained, the point is your governing capacity is MS. If it's not continuously laterally restrained, it means it fails the formulas here, then you've got to continue with the working to calculate what MB is. Okay? Okay, one important thing to note is when you are checking for full lateral restraint or not, there's a value for beta M that you need to calculate. Just note that when you're doing this, that beta M actually has different values. Okay, so for example, if for segments that have only transverse loading, beta M is equal to negative 0.8, a possible beta M value is also negative 1. And another possible value is, you can also take it as the ratio of the smaller moment on the top to the larger moment at the bottom. Okay, all of this is in the code. So when you're doing this check, just please remember to use the correct and appropriate beta M value for when you're doing the calculation. Okay, so that's step 9. You're checking for full lateral restraint. So if you don't, then you go on to step 10. Is determine the effective member length for bending. Okay. Now when you're determining the effective member length for bending, the couple of things that you need are effective length for bending LE. This is different from the gamma method effective length. Remember, the gamma method effective length was to calculate the effective length for compression. But now when we're looking just at bending, we've got a different set of rules to deal with. Remember, this is KT, KL, KR times the length. Okay? We use the appropriate tables to calculate what these values are. Okay? And we need to calculate what M naught is, the reference moment capacity. Now the reference value here, M naught, changes depending on the shape. So if you have an I shape with equal flanges, unequal flanges, etc., they all have different M naught. So just use the correct M naught formula. Again, it's in the code to calculate what that is. Okay? Now step 11. calculate alpha m, calculate alpha s. Okay, this is again from a revision from a few weeks back when you did beam design. Okay, same principle here, calculate alpha m, alpha s. Step 12 is calculate member capacity. MB is equal to alpha m, alpha s, ms. Now, depending on whether it's the x direction or the y direction, you need both, right? So for example, there's MB x, for example, alpha m, alpha s, ms x. You do the same thing for y. Now, one thing you need to remember is that when you're checking against m star, remember mx star is checked against phi mbx. Okay, but my star is checked against phi msy. This is really important. Okay, you check against the member capacity in the x direction, but in the y direction you check it against the section capacity. Okay, really important thing to identify that this is what you're checking for. Okay. Now just stepping through here, I'm conscious of the time, so I'll just step through quickly. You have step 13, which is calculate the reduced section moment capacity. So you check mx star lesser than or equal to phi mrx, where phi is equal to 0.9, and mrx is equal to msx, 1 minus n star over phi ns. Okay, so the reason why you're doing this check from step 13 onwards, the reason why you're doing this check is because that you're taking into account the fact that bending is not happening alone. Remember, if you have a look at the steps that we've done so far, step 1, 2, 3 is really your analysis stage. 4, 5, 6, 7 axial check. 8, 9, 10, 11, 12 bending check. From this point onwards, we're doing combined check. So checking the fact that both of these are happening together. So you check against the reduced x, and you also have to check my star lesser than or equal to phi ms or mry. And remember, phi is equal to 0.9 here, where mry is equal to msy, 1 minus n star over phi ns. Okay, remember, these values depend on n star. So remember, in step 1, when we are collating which n star and m star we're going to use, if there are two n stars we're going to use, one is from combination A and the other is from combination B, then this will yield two different values, right? So we'll need to do, for combination A, MRY is going to be this. For combination B, MRY is going to be this. You need to remember, MRY is a capacity value, yes, but it's not just dependent on what it is. It's dependent on how much load you're putting on it. MRY changes based on how much load is applied. Okay, you've got to keep this in mind. All right, that's step 13. Now finally the last step, step 14. I'll write step 14 on this side because it's slightly long. Step 14 is, now you've got to do one last combined check, okay? To do this combined check, there's a bit of a flow chart that I've used that I find easier to understand. So you ask yourself, is the member bending about the x-x axis? Okay, you ask yourself that question. If your answer is yes, let's start with no first. If the answer is no here, then check in plane capacity requirements. MIY equals to MSY 1 minus n star over phi NC. where phi is equal to 0.9. Okay, this is a simple check. So if your member is not bending about the x-axis, which means it's bending about the y-axis, if that is the case, then the only thing you have to check is the reduced section capacity MIY, just based on MSY and your phi n star, your n star and your phi n c. Remember, phi in this case will be 0.9. Now, if your member is bending about the x-axis, then there's two checks that you've got to do. You first have to ask yourself, is there sufficient restraint to prevent torsional or lateral torsional buckling? Okay. Now, just note that lateral torsional buckling here is not the same as column buckling. Lateral torsional buckling is the type of buckling that's specifically for bending. It's flexural failure, flexural buckling. Okay. So you've got to ask yourself, is there sufficient restraint to prevent lateral torsional buckling? Basically, what I'm asking here is MB equal to MS? Right? Is it continuously laterally restrained, or is it not? If MB is not the same as MS, then you have to, there's a yes, no here as well. So if this answer is yes, I'll write this down first. Then you check in plane requirements. MIX equals to MSX 1 minus n star over phi NCX. And then you check MX star lesser than or equal to phi MIX. Phi is equal to 0.9. If the answer is no, I'll just write it out here. Okay. Basically, if there is sufficient lateral restraint to prevent torsional buckling, if the answer is yes to this question, then this is the formula that you use, okay, to check for in-plane bending, etc. And you're checking against MIX. Now, the important thing to remember here is, what is this NCX value? NCX is the compression capacity of your column. But remember, it's not the same as this. These are not the same. This is, remember, this is a very common mistake that's made by students. This NCX needs to be calculated with KE equals to 1. Okay? Extremely important. That means it's the compression capacity of the element without taking into account the effective length factor. Okay? KE is equal to 1. Same thing here. So by the way, phi is equal to 0.9, you check that, and if that is clear, then you're done with the question. If there is sufficient restraint to prevent, if there isn't any sufficient restraint to prevent lateral torsional buckling, which means you don't have continuous lateral restraints, it's going to buckle, etc., then you use this. You have to check both in-plane bending and both out-of-plane bending. Just remember, same thing, NCX here, NCY here, both are KE equals to 1. You have to recalculate them. It's quite sneaky, but you know that's the check that you have to perform. Okay. Now, sorry, that was step 15 as well. Step 15 is you've got to ask yourself, is the beam column under biaxial bending? Okay. Now I want to be very clear here. Biaxial bending means that the column has an applied load in both directions. Okay? It does not mean that it's buckling in both directions. Okay? Remember, biaxial bending means that you're applying stresses. That means your wind is coming from both sides. Right? You have a column. There's a wind blowing in the north-south direction and in the east-west direction. Only under that case is it biaxial bending. If there's only applied load in one direction, like an applied wind load in one direction, then this doesn't apply. Okay? But if this is the case, so if it's no, then you're done with the question. If the answer is yes, there's one more pesky check that you've got to do. This is the formula that you've got to check. Combined bending in both directions, x and y, and which MCX do you use? It's the minimum of MIX and MOX. And that brings to a close your beam column question. Okay? Now, I'd recommend you practice this as much as you can. Okay? One beam column question will take you a good amount of time to get through. It's like an hour-ish. Okay? Try to get, that's a good timing. Do it. Yeah. 1 hour. Okay? Or slightly longer, in fact. Okay? Because generally, in the past, I can only tell you what has happened in the past years. In the past years, generally, when there were only 2 questions in the exam, one of them was a beam column question. It takes everyone ages to get through, and then the other one was something like a connection question or something. Okay. Now, although this is Brian's first year, doing the course at UNSW, which means the past exams may be in a different format to what you're going to get this year. So we don't really know, right? Again, your best bet would be to listen to exactly what he said in the lectures. But I'm just saying, if it's 2 questions. Like a beam column question takes you ages to get through. Okay. Now before, before you go, I have access to a OneNote notebook that I've created, and when I've demonstrated this course over the last 5 years. Let me pull up the access code for it, and I'll give you the access code. It's got this entire flowchart in much neater handwriting. Well, not much neater, just a little bit neater. So you'll be able to understand. There's a bit more detail on it, and there's notes from the last few weeks. So before you go, please wait around, stick around for that. I'll give you the code, and if not, that's all. So thanks, everyone.
Thank you. Round of applause, please. Yeah, just a couple of notes. So one is the recording, which I guess I'll stop now.
Yeah.